Let me start. So yesterday we discussed these maximally symmetric spaces through this very elegant construction, which is the embedding in n plus one dimensional space. And I showed you that in Cartesian coordinates, the resulting metric can be written as a flat metric with p pluses and q minuses, and the curvature, which is plus minus 1 or 0, and then rho is the radius of your sphere, for example. Okay, so now these spaces, I showed you that they have n times n plus 1 over 2 Killing vectors, which is the maximum possible number a space-time can ever have. What I haven't shown you that all such spaces, all maximally symmetric spaces, can be written in this form. I just gave you an ansatz, and I showed you, well, the ansatz leads to this metric, and it is a maximally symmetric space. And I will not show it to you that at every, but the statement which is true is that locally, every spherically maximally symmetric space can be written in this form. Okay, so locally this is always true. You can have some weird identifications, you can have some weird global properties, but locally this is everything there is. Okay, so now let me, and so these spaces, they include some very, very important examples, S-sphere or hyperboloid, but also examples of ADSN or DSN. And so these are very, very important spaces. This guy is important for cosmology, and we will study it on Thursday's tutorial. And this guy is important for ADS-CFT correspondence, and you will study it in explorations in string theory. Okay, so now what I will use these spaces for, however, I will use the Euclidean part of these spaces, and I will use it as a building block for our space-time describing the universe. So part B, FRW space-time. And so we already established that observations give us that the universe is homogeneous and isotropic, but that's of course true for our spatial slices of the universe, right? So our universe is homogeneous and isotropic on spatial slices. That means it's actually maximally symmetric on them. Maximally symmetric on a spatial slice so I'm taking slices of t equal to constant, time is equal to constant, and the spatial geometry can, however, arbitrarily shrink or expand in time. And this will be described by a parameter which is called scale factor. So this shrinking or expanding is described by a scale factor, A, which is a function of time t. Okay, so what it means is that our metric for the universe is just minus dt square plus a square of t. And now the spatial part must be homogeneous and isotropic. That means maximally symmetric. So it's Gij 3, 0. It can have arbitrary curvature, G0, 3, 0, K, and dxi, dxj. Or, if you want, just expanding that formula here, it's just minus dt square plus a square of t. Now our eta has just pluses, so it's delta ij plus k xi xj rho square minus kx square. Okay, so that's the famous FRW space-time. F. And that stands for Friedman, Robertson, Walker, the three main guys in cosmology. Okay, sure. Yeah, there are more guys, but usually people call them this. Or sometimes they call them even Robertson Walker. But anyway, all the same. So this is the space-time describing our universe. So now we have three possibilities. So K is equal to 0, which means that our spatial thing actually has, looks like Euclidean space, and we call this a flat universe. If K is +1, then we have a sphere, and this is called closed universe. And if it's -1, you have H3, and it's called open. Okay. So one more remark about the geometry is that if you look at the metric here, there is some scaling symmetry. And you can exploit this scaling symmetry to set some of the parameters actually equal to something you want. So sometimes people choose to eliminate this guy, but I'll rather eliminate rho. So I will set rho equal to 1. So can set rho equal to 1. So the radius of the sphere in that embedding space will be equal to 1. And this is achieved by rescaling xi to be rho times xi tilde, and a will be scaled the opposite way, a tilde over rho. So by the scaling, you can always set rho equal to 1, and then this guy has the dimensions of length, and it will be the curvature of the spatial slice at time t. So then AT is the curvature of spatial slice. At time t. Okay, so far so good. So far so good. Okay, so now something you already know is the symmetries of this thing, but let me just make a small remark. So the symmetries around each point, the space is isotropic, so I can do arbitrary rotations around that point, right? So it's spherically symmetric. So it's spherically symmetric, or if you want, isotropic, which gives 3 Killing vectors for the spatial slice, and then is also, spatial translation invariant. Which is the homogeneity, and that gives another 3 Killing vectors. So in total, we have 6 Killing vectors here, right? 6 Killing vectors, and that they precisely correspond to the fact that the spatial part is maximally symmetric. It's homogeneous and isotropic. But what it also means, because A is an arbitrary function of t, at least at this point, then there is no symmetries like boosts or whatever. Right, so it definitely there are no 10 Killing vectors as Minkowski space has. Okay, so no boost invariance. So what it means actually that there is a preferred frame. And it's precisely that frame in which your space-time looks isotropic and homogeneous. And so this frame is associated with this freely falling observer, which I talked about yesterday, but people usually use the term co-moving observer. So this preferred frame is associated with the co-moving observer. And if you want, this co-moving observer is characterized by arbitrary time, which is his proper time. And he is not moving, or she, with respect to the cosmological fluid. So the coordinates xi are actually equal to const. So they don't change, they are equal to a constant. And it is only such an observer which is not moving with respect to the fluid, which sees the isotropic and homogeneous universe. So only this guy sees isotropy and homogeneity.
But this guy could be rotating, right?
Rotating, maybe. If you are rotating, probably some things go wrong, right? You are, maybe. But you see, so once I start messing with the time, right? So I'll induce, cross terms, dt, dxi, or whatever, and so then everything will break down. So I really have preferred time here, which is the proper time of this observer, and xi equal to constant. I'm not moving with respect to the fluid. Okay. So now, what about the scale factor? So in principle, the scale factor is an arbitrary function of time, right? But in practice, this is of course not true because we haven't imposed any constraints. We haven't imposed any dynamics. So of course, the dynamics of the universe is governed by the matter content in the universe. So the evolution of this scale factor depends on matter content of the universe and is determined through the Einstein equations. So now people like to introduce, well, at least one, but perhaps two parameters which characterize how this scale factor actually behaves. So one of them is called h. To celebrate Hubble, it's called Hubble's expansion rate. And that's the one I will use all the time. And then there is another one, which is called the acceleration parameter. And sometimes people like it, but I will not really use it. But just somebody tells you I'm using the acceleration parameter, then it's this quantity here. So whereas the Hubble measures how the derivative of A behaves, this guy is interested in how two derivatives of A actually behave. And that's called the acceleration parameter. So why the acceleration? Because until very recently, people thought that universe is actually, so it is expanding all the time, but this expansion is slowing down, so it's decelerating. So that's why, this guy was negative, and then you got Q positive. So that's why deceleration, you could call it acceleration parameter as well, but historically it's called deceleration parameter. Okay, questions? So now a boring part. So of course, these coordinates are very nice, and they are sort of like Cartesian coordinates, but people don't use them very often, and they use other coordinate systems. So let me just rewrite the metric in other coordinates, which are used more often. So first, spherical coordinates. And they are introduced like if xi were indeed the standard Cartesian coordinates. So you define x1 to be r sine theta cosine phi, x2 to be r sine theta sine phi, and x3 to be r cosine theta. Okay, so if you do that, then your metric is the spherical form where the omega square is just on the sphere, the metric element on the sphere. So it's d theta square plus sine square theta d phi square. Okay. So this coordinate system is often used. But even more often, people introduce a new radial coordinate. Okay. So new radial coordinate. And that's done chi, and that's done as follows. So you take your r, which is this spherical r, and you distinguish three cases. So it's either sine chi, or it's sine h chi, depending on k. Okay. And so if you do that, then your metric element takes the form minus dt square plus a square, d chi square plus sk. Okay. This I define to be sk of chi. Sorry for that. So this is a new function s, which is this, or that. So it's sk square of chi d omega square. Okay, so that's the second coordinate system which people use. So now, interestingly, which coordinate, chi or r, do you think is actually more natural from the embedding perspective and from the three-dimensional perspective? What do you think? So one of them is sort of like if you are a high-dimensional person looking at your space-time from this n+1 point of view, and the other one is more natural from this n-dimensional point of view. So, okay, so let me give you an example. So I just consider the closed universe, which I can actually plot as a sphere. So this is my n+1 dimensional embedding. So this will be x4. The person will be sitting on that sphere here. So there's a person here, okay, which can crawl along that sphere, right? And that happens at r equals to chi equals to 0. So you always place yourself in the origin of the coordinates, right? So that's why we are here at r equal to chi equal to 0 here. Okay, so now what you can show is that the following thing is true. So the radius of the sphere is 1. So this is our rho. We set it equal to 1. And if you look at the transformations, so r is sine chi, the following is true. So this is r, and this is chi. Or if you want, because this is 1, this guy is chi as well. Okay, so we have r equals to sine chi. So now you see that r is something which lives in that high dimensional space, if you want to. So r is more natural from this embedding perspective. So this guy is natural from embedding perspective, whereas the chi, it really measures how far I have to crawl on the sphere, right? So chi is much more natural from the FRW perspective. So this guy is natural from 3D perspective. That's why people like chi more than R. Okay, because it really measures how far I have to go in the universe. Okay, so we are still not done. There is one more coordinate system, so C, and that is basically, so we are happy with chi, but we are not happy with T. So we change T to something which is called conformal time. Eta. And that's simply introduced by saying dt equals to a d eta, or in other words, eta minus eta. So this is my definition. So eta minus eta 0 is just an integral from t0 to t dt prime at prime. Okay, and so if you do that, so plugging dt, so dt squared will now be a squared d eta squared. So I can factor the a squared out of everything. Okay, so then I have that d squared equals to a squared now as a function of eta, and then minus d eta squared plus dr squared 1 minus kr squared plus r squared d omega squared, or a squared eta okay, so that's the last form often used for FRW spacetime. So now, what is it? So here, so if you look at, for example, k equal to 0 case, so then this form of the metric is very, very suggestive. You have minus dt squared plus dr squared, and then s is just chi. So you have chi squared d omega squared. So what it is actually inside is Minkowski, and it's just rescaled by this factor. So for k equal to 0, you have actually stretched Minkowski. So now, as you will learn, actually k equal to 0 is almost the case which happens in nature. So we have basically Minkowski up to some stupid conformal rescaling. Okay. Okay, so these are the coordinate systems often used for FRW space. Let me just make a, well, stupid remark. So consider let me call it physical distance. Well, it's not really a physical distance, but it's more physical than the other distance. Physical distance. So no matter which coordinate system you look at, you see that always your co-moving coordinates, which are, for example, the xi or the chi or whatever, are multiplied by this a squared, right? So in some sense, I will call the coordinate distance by the value of the coordinates xi, and that's unphysical. Or I multiply it by this a, and then I'll call it physical. Okay, it's whatever. So physical distance. So you define xi physical to be a of t times xi, for example, in the Cartesian frame. Okay, so if I do this, then the physical velocity It's just a derivative of this, right? I can use anytime I want, so let's use t. So let's define this as vi p to be dxi physical over dt. Okay, just definition of the velocities. And now, obviously, I have two terms, right? I have to differentiate this guy, and I have to differentiate that guy. Well, in principle, the xi can depend on time, right? I can change xi. I can move through the space, right? So I have two terms. So this is equal to a times dxi over dt plus a dot times xi. Okay. So now you define the first one. So this guy you define to be vi speculator. So this is equal to a times vi speculator. And the other one I can divide by a, and I can return a. Okay, I have done nothing. So this is just h. And this is back my physical distance, right? xi physical. So it's a times the speculator plus h times xi physical. And this is vi physical. So I'm not doing anything difficult, right? I'm just differentiating two things. So now this is, as I said, this is called peculiar velocity. And it describes how the coordinates change, how the co-moving coordinates change, right? As I move through the space-time. So it means basically, so how the object is moving with respect to a co-moving observer, right? The other one is called Hubble's flow. And so even if the object were not moving with respect to my co-moving observer, this sort of describes the expansion of the universe, right? So how the physical distance is changing if I sit on a given coordinate. So I have two objects separated by co-moving coordinates, and how fast they are going apart. That's what the Hubble flow actually describes. Okay, so that's just a remark here. So now let us study in more details. So this will be true for any motion, but let us concentrate on the simplest possible motion, on a geodesic motion. Okay, so let us study what happens with geodesics. And of course, that's very useful to know, because in some sense, if there is no local gravitational attraction between, let's say, two galaxies, they sort of behave like if they were independent and moving on a geodesic. Or if you send a signal from a galaxy, let's say a light, then it basically follows a geodesic. Right? So let's study the geodesic motion. So motion of just particles. So you can always, so I'll talk about momentum and stuff like that. So basically I can absorb always the mass into the velocity to create the momentum. So I can choose an affine parameter lambda such that the momentum is just a derivative of my coordinates. So it's the form momentum. Okay, so it's not a velocity, but it's a form momentum. So basically what you are doing is that if you have a massive particle, you are absorbing m into lambda. So for a massive particle, so the proper time of a massive particle would be something like m times lambda. It's just a constant rescaling. So that I don't have to drag this m here. Well, I'll drag it anyway. Okay, so if you have that, then you can calculate what p square is, right? And so using our metric element, for example, this one here, it is equal to minus p0 square plus a square gij, 30, and k, and then pi pj. And, well, this is normalized, so it must be equal to minus m squared. I hope it's true, probably true. Okay. So now, this is the zero, well, the energy, if you want, of the particle. And this is the spatial magnitude of the momentum. So you can define this guy to be big p square, which is the magnitude of the spatial momentum. Okay, so far so easy. So another thing is that I can differentiate this equation. Okay, so if I differentiate with respect to, so now what I want to do with respect to lambda. So differentiating this guy, well, it's just a constant, so that's 0. So d over d lambda gives that p0 prime plus p prime equals to 0, or I want to evaluate this equation for p0 prime. So from here I have that p0 prime equals to, is there a minus sign missing? Equals to p prime over p0. Okay, so that's our equation 1. And it's just, yeah, quite simple. So now the second step, well, this is true for any particle. So now we have to study geodesics. So this is your geodesic equation. But of course, this is equivalent to, I don't want to calculate Christoffel symbols. So let me do it through the Lagrangian. So this is equivalent to Euler-Lagrange equations for L given by 1/2 g mu x mu prime x nu prime. So by the way, by prime I mean d over d lambda. So this is what I mean by prime, and by dot I'll have d over dt. Okay, it's just to distinguish lambda and t. Okay, so this is certainly true. It's a general statement, but it's usually faster to write down your geodesic motion from the Lagrangian. So in particular, I can write down the Euler-Lagrange equation. So okay, so let me specify what L is first. So it's 1/2, and again, it's this metric here. So it's minus t prime square plus a square of t, and then gij 30k xi prime xj prime. So this is L. So now let's take Euler-Lagrange equation. So now I have 4 Euler-Lagrange equations depending on which coordinate I choose. So let's choose t. So then I have dl over dt. Well, the only thing which depends on t is this guy here. So it's a dot gij 30k and these guys are, by my definition, just pi pj. Okay, pi and then pj. So again, I'll borrow 1a and I will divide by 1a. So I'll put a square here and I divide by a here. So I get a Hubble again. So this is Hubble. So this equals to H A square Gij 30K Pi Pj. And if you look at the definition of the spatial momentum, it's precisely the spatial momentum, right? So this guy here is just the spatial momentum. But on the other hand, this is equal to dl over dt prime, right? Because that's my second half of the Euler-Lagrange equation. So now the only thing which depends on t prime is this guy here. So this is minus t prime, but t prime is p0. So minus p0 prime. So I have an equation that h p square equals to minus p0 prime. Okay. Okay, so I can continue that equation. So using that equation 1, so this is equal to equation 1. So it's minus pp prime over pp prime over p0. But this is dt over d lambda, and this is, well, this is dt over d lambda. So now I can change from lambda to t. And this is just pp dot in terms of t. It's just a chain rule. Okay? Very good. So this is still equal to, so let me just write whatever I had here. So it's hp squared, which is a dot over a p squared. Okay, so now of course I can divide by p here and destroy the p there. So I have an equation that dp over p is minus dA over a, or in other words, p is just proportional to 1 over a. Okay. Very simple, isn't it? So now this equation is very, very important. So the derivation is very simple. The equation is very, very important. So now this was true for massive or massless particles, doesn't matter. It's just we use that they move on geodesics, and then we use this parametrization. Okay, so let's do first non-relativistic particles. Relativistic particles. So for non-relativistic particles, the spatial part, the magnitude of the spatial momentum is, well, it moves non-relativistically, so there's this mass, and then this will be the magnitude of the peculiar velocity. If you look at the momentum as we define it how the co-moving coordinate changes with respect to time, right? So the velocity has to be the peculiar velocity. I'm interested how the coordinates change as the particle change. Okay. So what it means, if I look at this guy, well, m is just a constant. That means that V peculiar actually goes like 1 over a. Okay. This is called a Hubble track. So what does it tell us? So it means that if a particle, consider any particle, consider a galaxy, and consider how the galaxy moves with respect to the co-moving observer, with respect to the cosmological fluid. So what this equation tells you is that the bigger the A is, that velocity is actually smaller. So of course we know that the universe is expanding, so A is getting bigger and bigger, so that galaxy will have smaller and smaller peculiar velocity. So the expansion of the universe actually tends to stop motion with respect to the co-moving observers, right? So what it means is that particles, meaning galaxies, left on their own, converge onto the Hubble flow, and their peculiar velocity actually decreases. So the peculiar decreases due to the expansion of the universe. Okay, so now what is actually true is that if you look at the universe at this point, then the random object, meaning random galaxy, random group of galaxies or whatever, will have V peculiar about 200 kilometers per second. Okay, so random objects have V peculiar about 200 kilometers per second. But later on, this velocity will be much smaller. And of course, you have to take this peculiar velocity into account, for example, when you were Hubble and you were measuring how fast the other galaxies are going away from you. You have to take into account that you yourself actually are not the co-moving observer. You are moving with this random velocity, sort of, right? So you have to subtract that result. Yes?
So if a particle has an initial peculiar velocity, whatever it is, this will scale in such a way.
Exactly.
So I shouldn't think about it as this thing creates some kind of peculiar velocity. So
well, it actually destroys the peculiar velocity, right? So you start with a particle which moves, with its arbitrary velocity with respect to the co-moving observer. So what I'm saying is that this velocity will eventually be zero. It will eventually decrease as the universe is expanding. Yeah, it's not generating that velocity. It's actually dim. Yeah, if you start with that velocity, you go down. So now, what is also obvious is that if you have the co-moving observers, which means that they have their xi equal to constant, then the coordinate distance between these co-moving observers is not changing, right? So xi, this one is xi equal to 1, this one has xi equal to 5, so they are still there. But of course, because the physical distance is multiplied by this a, right? Then the physical distance between the observers actually is increasing as the universe expands, right? And so that's why we say that the universe expands. Okay, so I don't know if I should say so co-moving observers, just note, co-moving observers have the same coordinate distance, but the physical distance increases proportional to A. And that's why you say the universe is expanding. Okay. So this is what happens in the non-relativistic case. So let us look at the relativistic case, which in some sense is even more interesting. So massless particles. So for massless particles, you know that whatever the momentum I wrote somewhere there, so m squared equals to 0, so p0 squared equals to p squared. Okay, so p equals to p0 choosing the right root equals to the energy, and you know that the energy is proportional to the frequency. Okay, so now you know that p is proportional to 1 over a, so the frequency is proportional to 1 over a. Or lambda, which is 1 over frequency, is proportional to a. Okay, so that's the conclusion you make for relativistic particles, and this is called cosmological redshift. Okay, so what it tells you is that if you send a photon this way, and later on, an alien observes that photon will have smaller frequency because the universe expanded. Okay, so everything is getting redshifted as the universe expands. Okay, so to quantify this, let's introduce a redshift parameter. Well, that is lambda observed minus lambda emitted over lambda emitted. Okay, that's how the wavelength changes. So now let me consider a situation that, well, lambda observed is whatever we observe here and now on the Earth. And lambda emitted is, well, the emitted photon at the time when it was emitted from some galaxy. So lambda emitted distant galaxy. Okay. So now the trick is to expand. So you know this. So you need to know how A behaved at T1, how A at T1 is related to A at T0. But of course, you do the Taylor expansion. So A at T1 is A at T0 plus the derivative times T1 minus T0. But let me just put A T0 in before that. T1 minus T0. And then you have A derivative at T0 divided by A at T0, which is again the Hubble parameter. So it's H at T0. Okay, so that's my Taylor expansion, which means that Z, which is A at T0, A at T1 minus 1, from this definition and using that relation here. So now you plug for AT1 this guy here, and you treat that T1 minus T0 is small. So you can move it from the denominator to the numerator. And so what you get from here is just this is equal to T0 minus T1 H0. Okay. However, of course, C equals to 1. So what really stands here is C times T0 minus T1, which is the distance between, if you want, is the physical distance between the galaxy and you, right? It's really the distance the photon had to travel in between these times, sort of, right? So this is a physical distance. Let's call it D, the physical distance. Well, let me put this thing, because there's so many distances you can define in cosmology, and they all differ, and they all are sort of very vaguely defined. So yeah, so this is another vague definition of physical distance. But anyway, so what we got is Z is equal to H0 times the physical distance. Okay, so this is a famous thing which Hubble observed, right? So what he noticed that if he's looking at distant galaxies, actually their spectrum is redshifted, and it's redshifted proportional to the distance of the galaxy. Okay, so by the way, H0 is the Hubble time. Is the Hubble parameter at, well, today, at time t equal to 0. So nobody knows what it is, so that's why people like to, well, it's given by observation, but the uncertainty of that observation is hidden in small h. So it's 100 times small h, and then it's measured by kilometers per second per megaparsec, where the current observation for small h is just 0.67 plus minus 0.01. Okay, so basically what it tells you that if a galaxy is distant 1 megaparsec, then it's moving 100 kilometers away from you, approximately. Okay. So what it means, as I said, is spectra of distant objects are redshifted proportional to their distance, and this was first observed by Hubble. So what he actually did is that he measured the spectrum of these galaxies. So he measured Z, but he interpreted that Z as the fact that the galaxies are going away from you. So he interpreted that as a Doppler shift. Okay, so by Hubble interpreted that as a Doppler shift. Due to the fact that actually the galaxies, when they emit the light, are going away from you. Okay, galaxies go away. Okay, so now if you open Wikipedia, you will find that for small velocities, the redshift is proportional to the velocity. Okay, so Z is actually V over C. So C is 1, so it's V. So you have that thing is V is equal to H0 times T. So he said that the galaxies are going away at a speed which is proportional to their distance. So it seems like, if I look at this direction, it's going, the further it is away from me, the faster it's moving. So it seems like all of them started at one point, sort of, and then they are moving in, all possible directions. Of course, doesn't mean that they started at a point. If I return back to my favorite picture, so here is a person on that sphere, and then you have a galaxy here, for example. So then the physical distance is this guy, and he said, well, the velocity is going that way, and then if I look at another galaxy here, that will be going that velocity, and if I'm twice as far, it will be going this twice as much velocity. Okay, But of course, it doesn't mean that we sort of all started at one point. It means that you are blowing up the balloon, that the balloon is actually getting bigger and bigger. So it's an effect of the expansion of the universe. Okay, so now, okay, questions? Well, maybe just summary. So you can understand this formula z equals to h0 times t in two ways. So the right way, I would say, is the GR point of view, where you simply say, well, it's due to the cosmological redshift. Cosmological redshift as A is getting bigger. And the other way is due to Hubble, who said it's this Doppler shift. Due to the fact that the galaxies are going away. So there's some velocity v for the galaxies which go away. So whereas this interpretation, of course, is correct for any possible redshift. So this is just a mathematical identity, right? So we derive it exactly, well, almost exactly. Then, the interpretation through the Doppler shift is not so obvious if you go to higher and higher Z. And exactly because you don't know how to define really what it means physical distance and what it means other things. Okay, so questions?
What about higher order terms? Like you could see you get continuous expansion and then you get a double dot. So you would expect that galaxies further away they would somehow see the acceleration rate.
Yeah, you need to go to higher. Yeah, exactly. You can go, well, you can tail expand to any order, but the question is, what it means physically. So what can I observe? Can I measure still the distances? The big problem in cosmology is measuring the distances, right? So there is something which is called, astronomers use things like standard candles, right? So you assume that there is a galaxy which has constant luminosity, and you know that luminosity, and so looking at that galaxy, how faint it looks to you, you say, well, that distance is away. Another thing is that astronomers use standard rulers. So for example, if you know how big the object is, for example, how the big typical galaxy of this type is, and you measure the angle under which you see it, you can measure this angular distance, right, and so on. But they all give different results. They all depend on this redshift. And moreover, they are not well defined because, of course, the galaxy doesn't have always the same luminosity, and it doesn't have always the same size, and so on. So there's a big problem how to measure properly distances. And so one of the reasons, one of the things actually people thought that maybe there is no dark matter and dark energy at all is that because all that is based on is the measuring of distances in some sense. And if you don't know how to measure distances properly, maybe there is no dark energy. Okay. So let me stop here and we continue tomorrow.